Thanks for coming on tonight. So I've just been told no food in the auditorium, so if you have any pizza or anything, I guess you have to eat out there. So I just wanted to start off by thanking Penn Medicine for hosting the event for us tonight. And from Penn Medicine, I have here Pat and Mike. We're going to give a little talk and then we'll get going.
Okay, we won't all joke too much, but really looking forward to having DataPhilly here. I mean, I assume everyone here has could admittedly love data in some way, right? Regardless of the industry. And likewise at Penn Medicine, more data driven and more data hungry. And so, you know, making self-promotion here, make sure you know that we have open spots within our own team, different teams across Penn Medicine. Penn Medicine is about 30,000 employees, but specifically in technology area, so there's the IT team, maybe 500 people, and specifically we have a data analytics team, which Frank is the front row there. Our team, probably about 40 people and growing, and there's also a development team, probably another 30 people, and on the school management side, also need help on the IT side. So, but the balance in terms of what help we need, we definitely need help. And also the science team, which Mike will go through much of some of the needs they have, but whether it be mobile applications, whether it be data engineering, whether it be analyst work, it's all from, you know, we've had crazy questions from how exactly do we figure out if it would help be preventative for colon cancer if we gave 3 Uber rides for colonoscopies, to how do we find out what's the next mutation or variant that would help, you know, eradicate cancer cells of maybe all cancers. So it goes from all ranges. You work with interesting people, but if you or anyone else has interest about anything we're doing here, then we have a career site. But for me, you can just reach out to Patrick Farrell, just on LinkedIn, find it, Penn Medicine, and connect that way. And here's Mike.
Yeah, thanks. So I'm the chief data scientist for the data science team. Work really closely with Pat's team, data engineers, getting the enterprise ready to go. We build predictive analytics systems for predictive healthcare solutions. So predicting when someone might have a heart attack or crash from an infection, or they're not going to show up to their appointment. But really meaningful stuff, a lot of fun. And if you have more questions, definitely reach out. Thanks.
Thanks, guys. So up tonight we have a pretty awesome talk. Rachael and Tony are going to be talking about their work on the Large Hadron Collider. And without further ado, I'll hand it to you.
Let me just. Hi, everybody. So my name's Rachael Krieger. I'm a graduate student at UPenn, and I've been working on LHC physics for about 4 years now. Today we're going to give a talk kind of summarizing the challenges of collecting and processing data at the LHC. As kind of a motivating example, if you think about, you know, what are the most fundamental things that make up the world we see around us, all the visible matter in the world. Someone more artistic than me might say it's like colors and lines and shapes. A chemist would probably say various elements from the periodic table. But if a physicist were to summarize the most fundamental components of the world around us, they would talk about the particles of the Standard Model. The Standard Model is a theory about these most basic elements of the universe. So in this diagram, this is kind of an artistic rendering, but you can see there's 3 colorful boxes. So there's this sort of pink box is the quarks, which have fractional charge and combine together in pairs or triplets to make up more stable particles that you might be more familiar with, like protons or neutrons. So these don't really exist on their own. They always want to exist in pairs or triplets. Down here in this green box is the leptons, which have integer charge. Well, they have plus or minus 1 or a 0. And so these can exist on their own. They don't need to be with another guy. And you're probably pretty familiar with the electron and its heavier cousin, the muon, maybe. And then this purple box is the force carriers. So these are particles that carry the fundamental forces, like the strong force is carried by gluons, and the strong force is what binds protons together. The photon is the carrier of the electromagnetic force. And then in the background, you see this sort of gray blob with a field all around it. And this is supposed to represent the Higgs boson. The Higgs boson was in the news a lot about 2 years ago because it had finally been discovered at the LHC. And the discovery of the Higgs boson was a real triumph for accelerator physics, because the Higgs boson had been predicted 50 years before, and people knew it had to be there. Because the Higgs boson is it really ties this whole picture together. And so finally, putting in this last important piece of the picture was a really big deal. But I mean, maybe you just don't care about science theories and you're like, well, okay, so it's another particle, what's the big deal? We really need to study the Higgs boson to understand all these particles, because the Higgs boson is what gives these particles their mass. And mass is a very important, very fundamental property of particles. So to give a quick sort of ad hoc explanation of how the Higgs boson gives particles mass, I'm going to use kind of a funny example. So if you imagine there's a dinner party or a cocktail hour or something, and there's a bunch of people hanging around just talking, and say somebody wants to walk through the crowd to get to the bar on the other side. If just some ordinary person tries to walk through, like me, let's say, come on, click. It's not going.
It's going up
there.
there.
It goes. Oh no, it's not going down here. So if I go through really fast. If a famous person like walked into the party, everybody's going to want to stop and talk to them, and it's going to be a lot harder for them to get through the crowd. And so this kind of models the way that the Higgs field, so the Higgs field is all these people, gives particles mass. If a low mass particle like me goes through, the Higgs field doesn't interact with me very much. And so I have really low mass. And if somebody who interacts with the field a lot goes through, it gives them a lot of mass. And so this is how we understand the masses of particles. And so now I'm going to pass to Tony for a while. He's going to talk a bit more about how we actually measure and find particles. Let's see. There you go.
All right. Hi, I'm Tony. I'm also a physics grad student at University of Pennsylvania. I worked on ATLAS, which is one of the experiments at CERN, for about 4-ish years now also. But I'm currently in the process of leaving the field since I'm not really looking to finish my PhD. So if I go on here to more, so particle collisions. In order to find new particles such as the Higgs, we want to smash known particles together, which is protons in the case of the Large Hadron Collider. This makes use of Einstein's famous equation E = mc squared, since we have the energy, really high energy particles smashing together. the energy from the collisions turns into mass, and voila, you have brand new particles. So this is what we do in high energy physics. This is a TLDR of how to win Nobel Prizes. First, you build something that smashes particles together. Then you smash the particles together. You detect what happens when you smash those particles together. You collect some data from smashing those particles together, and then you analyze the data collected from smashing those particles together. And of course, then you have found new particles, and you get your Nobel Prize. So starting from the beginning, not the beginning of collider physics at least, but the beginning of the Large Hadron Collider. It was known for a while that the Higgs was around this certain mass range that we wanted to be able to reach with a collider. So we wanted to build a smashing machine with enough energy to produce the Higgs. CERN just happened to have a large underground tunnel that was used for a previous collider experiment that I don't have time to go over, but this was an electron-positron collider, which, while it has a lot cleaner particle production, you cannot reach as high of energies. In 1992, so midway through the sort of LEPS program, the Large Hadron Collider started being planned to go in the same tunnel that LEP was already in. So they were going to disassemble LEP and then create the LHC in the place of this. And the Large Hadron Collider was to be a proton-proton collider that can reach much higher energies than LEP. So this is 14 TeV versus 209 GeV, where GeV is billions of electron volts, which is a unit of energy, and TeV is tera electron volts, which is trillions. So it has a much, much higher mass reach and much more exciting physics possibilities beyond even the Higgs. And then a fun little history fact, in 1993, the US Congress canceled the superconducting super collider, which was to be a 40 TeV proton-proton collider, which was about three times as energetic as CERN, but they decided to cancel it midway through construction after they already spent $2 billion. And this could be an entire presentation of itself, why this was canceled, to say the least. But it ended up being very, very expensive, and Congress did not like it. And it was to be built in the middle of Texas, which isn't the best place to like form a scientific collaboration. Then in 1997, US was officially admitted as a CERN observer state, which just means that they can work there and provide some funding to CERN. Though, of course, many of the US physicists had already jumped ship to CERN immediately after the SSC cancellation. And some already worked at CERN at the time. And also in 1997, the ATLAS and CMS experiments were approved. And these are large general purpose particle detectors along the LHC ring, which I will show you. And finally, in 2008, the construction was completed of the Large Hadron Collider, and we finally were able to switch it on. And this only cost the European Union and us about $9 billion, to put it in perspective. This is the Large Hadron Collider. It's a 27-kilometer ring that straddles the border of Switzerland and France. You can see Lake Geneva there in the background. Let's see, I have a Lake Geneva right here, and these are the French Alps, I guess. But we have a 27-kilometer ring with a few interaction points where we put detectors. Now, I worked on ATLAS, which is nice because it's closest to the CERN main site, so you just have to cross the street versus taking a car all the way over here. This is what most of the 27-kilometer ring looks like. It's all so the particles travel in the middle of this pipe, and then this pipe is surrounded by superconducting magnets that bend the particles to allow them to go in a ring. And then most of this pipe is all cooling, because these superconducting magnets need to be cooled down to about 2 degrees Kelvin, which is minus 270 degrees Celsius / Fahrenheit. It's about the same at that level. Yeah, so most of the tunnel looks like this, and you can ride your bike right along here if you really need to go for a while, and they have various machines that allow you to get from one point to another. So this is where it all starts. This is This is a little bottle of hydrogen that contains all of the protons that we've ever used for the LHC to collide them together. So we take those protons, we accelerate them through a series of bigger and bigger accelerators. So it starts here, we go through proton synchrotron, go to super proton synchrotron, and then to the LHC finally. We get to very, 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 very close to the speed of light of these protons, and then we collide them at various interaction points again. And of course, it's not really a perfect circle. There's alternating straight and curved sections, where the straight sections are used to accelerate the particles faster, and the curved section allow you to actually loop back on yourself so you can collide the beams. And this uses a very high constant magnetic field. So now we actually start getting to the data parts here. So we smash these protons together when they're going really, really fast, and there are bunches of 10 billion protons pass through each other that are about 10 centimeters long. This creates many, 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 many collisions, most of which are very boring, glancing blows, where we want the most energetic collisions, which happen when you hit two particles head on and energy sprays transverse to the beam line. And these collisions happen every 25 nanoseconds. So it's 400 million times a second. And we somehow want to get all this data out. And this is a picture of two bunches of protons coming in and colliding at various interaction points here. So this is all one event where multiple protons collide with each other. So step 3 in my little list was detect what happened when you smash these particles together. Now I'll focus on the detector that I know, which is the AtLAS detector, which is a large multi-purpose particle detector. There's also several other detectors that I know much less about along the ring. And just some quick stats of AtLAS. I'll show it in a bit more detail on the next few slides. But it is 46 meters long, 25 meters in diameter, it weighs 7,000 tons, there's over 3,000 kilometers of cable, and it produces about 16 petabytes of data per second, which is 50 zettabytes, I had to look that up, of data per year if we actually decided to be able to store all this. Of course, this is way too much data for us to actually manage to store. So we'll spend the rest of the talk discussing how we get this data down to an actual manageable level. This is the AtLAS detector. This is huge. You can see some people down here for scale. It's pretty much an onion where you have two bunches of particles coming in from either end and colliding in the center. And each section, as you go out from the center, gets less and less granular because you're trying to cover a larger area. You can't realistically spend so much money making it the same granularity all the way through. So different sub-detectors of this are designed specifically for detecting different attributes and types of particles. And just, you'll see this a bit later, but I worked on a section called the TRT, which is the transition radiation tracker, which is part of the inner detector that does the particle tracking. Oh, and this is pretty much the worst acronym of all time. Acronyms in acronyms. Well, this is a sort of cross-section of the AtLAS detector, where you can see that different types of particles, say protons or neutrons, make have a different signature in our detector, where the muons actually keep going all the way through, and protons and neutrons are stopped. Neutrinos just keep going forever. Photons and electrons are stopped down here, and all of the charged particles are able to be tracked in the inner detector. So step 4. Step 4 is by far the biggest step of this, where you want to actually collect the data from smashing particles together. And the goal is to pick the most interesting data and actually save it to disk. And the data goes through many, many systems before actually being written to disk, or in some cases, tape. So let's start from the top again. We start with collisions. This is the same picture as before. So we collide, we collide particles every 25 nanoseconds and hope that some of those are interesting. So the first step in slimming down this 16 petabytes of data per second is something called the hardware trigger, or level 1 trigger, where the goal of this system is to reduce the data by enough to actually be able to move it off of the detector, move everything about the event off of the detector. It does this by determining if the event had a hard head-on collision, which are by far the most interesting, as I said before. Once it determines if this event is interesting, it sends a signal to all the sub-detectors telling them to send all the data about this event to the next stage to be slimmed further. And this step reduces the event rate from 40 million events per second to about 100,000 events per second. So it's 1 out of every 400 events. I have further information about this on this slide, where the hardware trigger takes a subset of information from the Atlas detector that looks if there's high energy deposits not along the beamline. So again, from one of these head-on collisions, we expect particles to jet out in a plane that's transverse to the beamline. We do this with a lot of custom analog electronics, field programmable gate arrays for anyone who knows hardware. This is located in a server room about 100 meters away from the detector. And this system needs to make a decision to whether or not to keep an event in 2.5 microseconds. But remember I said that this is 100 meters away, and signals can only travel at the speed of light. So most of this 2.5 microseconds is actually taken up by just the signal traveling from the detector to the server room and then back to the detector. Since it takes about 1 microsecond for a signal to travel in for it to travel 200 meters in perfect fiber optic cable. And of course, no system is perfect, so we need a little bit of leeway. Oh, and I have the approximate bandwidth of these systems here. So it takes about 2 terabytes or 2 terabits per second. There's 2 terabits bandwidth between the detector and the server room in order to quickly determine whether or not this event is an interesting event. So then it passes this signal to the sub-detectors whether or not to keep this event. So let's take one particular example subsystem for this, the transition radiation tracker, which is a system of about 400,000 little tiny straws about this long that you can tell whether or not a particle passed through them, and you can use the data to construct a particle track, which helps you determine what kind of particle it is and its mass. And so this is the beamline in this, and particles collide around here and go through a couple different layers before getting to the TRT. And just some quick stats about our data acquisition system. It has about an 8 terabits per second collection rate that it has to sort through, and it can only send about 50 gigabits per second out of the system. This is done with a system of over 3,000 custom electronics boards. Like I said, we have over 400,000 individual straws that each need a readout line to be able to read out that data to the outside of the detector. Now, to control all of these boards, we have about 150 lines of pretty darn terrible C code, in my opinion, but I only inherited this system, and about 300,000 lines of XML configuring files used to control this system. I should mention that all of these are not the same type of board also. There's about 100 just different types of boards that you have to account for in order to properly model the system. So these are some of the FPGA boards we use for receiving the hardware trigger and actually read the data out of the detector. We have about 144 of these in total, and we use 10 computers to control them. This is a VME bus crate. If anyone actually has to use this terrible technology, I'm sorry. So this is an example event. that say an event is determined to be interesting by the hardware trigger. So a collision happens, an event passes the hardware trigger. Let's call this event number 7, which is numbered by the main LHC clock. Now, if you remember, I said we have over 3,000 boards, and you can imagine how hard of a problem it is to keep these boards all in sync with each other. This could be another talk in itself that I am not qualified to give because it's such a complicated problem. It would easily be an hour-long talk by itself. But going back to this event number 7, it passed the hardware trigger. So a signal gets sent to our FPGA boards that we need to keep this event number 7. These FPGA boards split up the signal and pass it to all of the boards on the detector, the 3,000 or so boards that are on the detector. So these on-detector boards receive the signal, and they have to look back in their buffer to retrieve event number 7. So each board can hold data for about 6 microseconds, which is enough time for the hardware trigger to make its decision and then further propagate the signal to these actual on-detector boards. They send this data about event number 7 back to the off detector, or back into the server room, which is off detector, to some more FPGA boards. These FPGA boards, we call them readout drivers or rods. They receive the data about event number 7 from many, many, many different on-detector boards that are all combined together to send to this one FPGA board. Then the data from event number 7 is compressed using a Huffman table encoding, which takes the most probable patterns determined from data taken previously and compresses the data. And this data can be uncompressed on the fly at later stages to view the physics information and be able to make calculations about tracks or anything you want. This data is then passed from the FPGA boards to a system that combines information from all of the detectors and packages that together to be eventually written to disk. So combining all of this data is also a task in itself. We have so data from subsystems are combined in standard PCs with specialized PCI cards, which are typically about 10 to 15 computers per subsystem, making a total of about 50 computers that do this combining. The data is then available for the software trigger, which we will go into in a minute, to make more sophisticated calculations to determine which events you actually want to save. Now I'll pass to Rachael here for more information about the software trigger.
Okay, so the software trigger is a little bit different from all of these hardware boards and triggers. The software trigger is basically just a computer farm, and what we really get to do is write the code and write the software that determines what sort of information we're going to keep. So you get to the physicists get a lot of input into what sort of events we're going to keep from the software trigger, because of course this is the last stage, and this is where we have the most time to make a decision about whether we want to keep the data or not. So let's say you're doing a search for the Higgs boson, and you want to design a software trigger to collect data that looks like what you want. So we really want to try to make our data really look like the signal we're expecting, because this signal is extremely rare. So here, this diagram here shows a process we might be looking for. So this is a Feynman diagram. It's not particularly important to understand everything about it, but you can sort of read it from looking from left to right. These P's are protons. They interact, and then they produce this pink Higgs boson. And then if the Higgs boson decayed to 2 Z bosons, and then each of those Z's decayed to 2 leptons. In the search for the Higgs boson, people called this the golden channel because it's because leptons are really, really nice to find. They're a lot easier to find than other types of particles. And I'll go into that a little bit more. So like I mentioned at the beginning, leptons have a full number charge, which means that they're not undergoing strong physics, which is really, really difficult to calculate. And so we can accurately reconstruct leptons anywhere from 70 to the high 90% of the time, depending on how strict you want to be. And so it's a really clean signal, which is great for a search because you don't want lots of other processes contaminating your data. And so if you wanted to search for the Higgs boson, you might want to use a lepton trigger to collect your data. And that's actually what they did in the search for the Higgs, is they used single and double lepton triggers. So the way you actually do this is the software trigger, which is called the high-level trigger. Basically, it takes data from the acquisition system and it looks for the level 2 part of the HLT, looks for where did interesting events occur, what place in the detector. And then it tells the data acquisition system, like, hey, I think something interesting happened here. And then the data acquisition system works with the event filter to reconstruct that event. So this is the part that's the slowest, you take all of these just hits and lines and things going through the detector and you try to connect the dots. You try to say, like, all right, I found some energy going through this spot. Is this an electron? Is this a muon? What is this? And so it's a lot about algorithms here. So you use these high-speed reconstruction algorithms. Then when you've reconstructed the event, you can write it out to your storage, which will usually be disk. One other thing you can do to control your high-level trigger so there's a limit, your bandwidth limited. You can't just send out infinite, huge amounts of information. And so you might want to control how much each trigger is writing out. And the way you do this is with a prescale. So you only take some certain fraction of events passing your high-level trigger. And you can adjust the fraction as you need, or your group. And then eventually it'll all come to a big storage farm like this, which incidentally is one of the only air-conditioned rooms at the Large Hadron Collider. So it's a good place to work. So then once we have the data, there's a data management system. In the past, we were using a system called DQ2, which was named after Don Quixote for some reason. And so for run 1, so the past 3 years, this worked really well. They saved a total of 160 petabytes of data, and they made it so that it could easily be broken down into smaller sets of about 600 million files, and thousands of users could easily download data sets on the size of gigabytes to terabytes to their own computers or their own personal storage. Now we use a slightly more scalable version called Rusio, which was named after Don Quixote's assistant's donkey. I didn't name it, which uses Oracle and SQL Alchemy. And then finally, we keep all of the data that we record. They don't, even when the analysis is done, they keep it around for a while in case people want to look at the data again. So if it's data that people are reading really often, we save it on a disk, but really old data gets saved onto tapes. And if you want data from a tape, it sends a request to this robot, which will find the tape for you and read the tape and send you the data. So that's I think that summarizes how the data gets from collisions to making a decision about what data is interesting to finally a disk or even a tape. So how do we actually find particles, right? This is great that we can collect data really quickly. That's all well and good. But I'm going to try to give a very basic description of how the Higgs was found in this golden 4-lepton channel. So this plot here, the x-axis it's really the energy of the 4 leptons that were reconstructed by all these reconstruction algorithms. And the y-axis is just counts. So we just count the number of events with an energy of 120 GeV per c squared, or whatever at various mass ranges. And then so you can see on this plot there's sort of colored, sort of smoother distributions, and then there's black dots with error bars on them. So the colors, these colored distributions, come from simulation. The red and the purple are simulated background, so events we're not really very interested in or events we understand really well already. And blue is what they thought the signal would look like, what they thought if there's a Higgs, this is what we should see. And the black dots are the actual data. So as you can see, the black dots go up at exactly the spot where the simulation thought a signal would be. So kind of the general strategy here is you collect your data, you subtract out the background, the boring stuff that you understand really well, and everything that's left is your signal. But how do we make these distributions to understand these, events that we've studied before? We use Monte Carlo simulation. So the basic idea is you make a simulator that that has all the properties that you want, and then you'll run it many times on random inputs. These simulations are extremely complicated because you need to simulate 10 billion particles passing through each other and then colliding and then passing through the detector, and then how would the electronics respond to having particles pass through them. So this is really computationally intensive, but we have a large grid of computers supported by universities all over the world, and so everybody shares the computing load. And then finally, the last thing we do to kind of understand these background events is look at control regions. So a control region is, the basic idea is you know what your signal should look like. You know where you want to find it. And then you just change one of the requirements. And then you look at what's going on there. So if you know your signal is going to occur at a particular position, then just look at a different position, but make all of your other requirements the same. So the idea is we don't expect any signal to occur there, and you can really understand your backgrounds then. So for the Higgs discovery, the data was collected using single and dilepton triggers. So they collected events that had been shown by reconstruction to have at least 1 or 2 leptons in them. They modeled the signal and background using a program called PowHeg and GG to ZZ. So these are Monte Carlo. And then based on what they had seen in the simulation, they could kind of know where they should look for a signal and then actually look for it. So that you make selection based on momentum and position. One thing I think that's interesting to note here is that in the past, LHC has actually been pretty behind on machine learning techniques for finding signals. So up until just a few years ago, all searches were purely cut-based. There was no, you know, you weren't having, you couldn't train your analysis to look more intelligently. But this is starting to change because it's becoming clear that you can't handle so much data with just these sorts of cuts. So this is a table summarizing the results. There's a lot more you can look at if you're interested in, but the basic idea is that you could, based on your Monte Carlo, if there were no signal, if there were no Higgs, you would know how many particles to expect in this particular region within some uncertainty that's both statistical and systematic. And then they look at how many things did they actually find there. And so you can see that the number they found was not within uncertainty, it was way out of uncertainty. And so they combined results from multiple analyses, and that in 2012, Atlas and CMS produced results saying that they had discovered the Higgs boson with a significance of 5.9 sigma. And it's important that it's discovered because you can't get a discovery in particle physics without at least 5 sigma, which if you like p-values is p00, it's really small. And so this was a huge deal because people knew that they knew this had to be there. They wanted to study this particle. They looked for it for so long. You know, a collaboration of scientists from all over the world helped to build this, the biggest machine that's ever existed. And then they found with enormous certainty that the particle they were looking for was there. And you can barely see it, but there's a, so that blue dot is the UPenn flag because all the UPenn grad students were there. So the kind of next things where CERN's looking to next now that the standard model has really been filled out, which is a great accomplishment. But of course, I mean, particle physicists need jobs, and you know, we've already built this great machine. Let's look for something more. So they're really trying to push right now. There's a lot of push in electronics, and there's a push for an even bigger accelerator, an even more powerful accelerator. But the thing that they're really trying to push right now is collaborations between the hardware experts and the machine learning experts within the collaboration. And CERN's trying to get in on this more. They do Kaggle competitions every once in a while. So if that's your thing, you should keep an eye out for it. And I think Tony as well, we're both very excited for the future, both in these new, you know, how can we push the electronics harder? And for me, more, how can we, you know, sift through and use the data we already have more? So I think that summarizes most of what we had to say. Do you guys have any questions? Yeah.
Very nice talk. A question I had is, you know, in the data science community, in the private sector especially, Bayesian statistics are, you know, very commonly used, but, you know, the particle physics community, it's not taboo exactly, but frequent statistics.
Yes.
Dominate. I was wondering if you could just, you know, like explain to the data science community, or not maybe physics baseball insiders, of why Bayesian statistics are not used as much within particle physics.
That's a good question.
Yeah.
I can't answer. Can you?
I think, yeah, I'm not really the most qualified to answer that. I think maybe that, at least for a lot of physicists, the understanding you get as thinking of things as like how frequently do things occur is a lot more natural, because that's really the language that physics is written around. And that's the way we think of things as, like how, like, oh, we're looking for, it to occur X number of times out of whatever. And so, but I do think a lot of it comes from maybe like previous training and just preferences within the community. Oh, sure.
I'm curious, how much data is there available to sift through now to look for stuff, and is it available to anyone? And what kinds of things are you looking for?
Yeah, so I think all of the run one data is available.
CMS released their
Yeah.
run one data.
So
It's like 300 terabytes of data.
yeah, CMS released, I think maybe this past summer, about 300 terabytes of data, and you can download it in much smaller amounts. You don't need to download the whole 300 terabytes. And all of the software that you would need to be able to go through that is all available. And of course, when they do competitions, they make data freely available. So if you want to take a look at it, you could go home and download some on your computer and take a look.
And there's probably many petabytes of mostly Monte Carlo data. We have so
Yeah.
much Monte Carlo data, and we
Yeah.
have so much more information about Monte Carlo since we
Yeah.
know exactly what was produced and everything.
Yeah, the biggest data sets by far are these simulations, because they contain a lot of information. Like the truth of what's going on. Of course, it'd be nice if you could just look in the data and ask, like, what sort of particle are you really? But, so you could get both data and Monte Carlo samples online.
And you said
Yeah.
some of your work is looking through that data. What kind of stuff are you looking for?
So a lot of what I do is when you make Monte Carlo simulations, no matter how hard you try, they're not going to be perfect. And so we do things to correct the Monte Carlo to be closer to data. And this allows you to, understand your background better and lower your uncertainty on how well your background is modeled, which is really useful for analyses. So I probably spend more time using Monte Carlo than data.
Higgs.
Oh yeah. Yeah, I have to say.
Yeah, I guess kind of two questions. That 150K of horrible C++ code and the 300K
XML configure
Yeah.
files.
Yeah.
Just made me wonder kind of how did you validate that it was actually doing what you wanted?
Here you go.
So we had before we even set up the detector in 2008, we had a piece of the detector in a room at the surface that we did a lot of validation of this code. We did it turns out you can use cosmic rays as a good sort of calibration tool. You get about 5 cosmic rays per second coming through something the size of your hand like this. So you can use that to calibrate your electronics and determine if your code is outputting everything properly, and if you can reconstruct events given what you collect.
And the other question was down the line, the software that you're working with. What are you using? What packages are you using? You said what you do, but like,
Yeah.
how are you doing it?
So most of the analysis software at CERN is written in C++ or Python. And we use a certain file format called root, which we use for storing information about histograms. And so a lot of what I do is usually reading information from root files and combining it together quickly. And then the other kind of part of what people do is a lot of work with the grid. So we have this huge, I want to say there's like on the order of 200,000
Computing nodes.
nodes. And so you also write packages to interact with this large computing system and do more complicated computations than you could ever do on your, because everybody has some like small little computer for their department. But if you need to do something big, you need to interact with this grid.
And you
So,
do that
yeah.
in Python or C++?
Yes, I think everything with the grid is in C++.
Yeah.
Um,
Even the back end of root Python is C++.
yeah, everything really is C++ in the end, I think. But
And root contains its own C++ interpreter, so it actually can live interpret C++ code with somewhat mixed success.
Are the reconstruction algorithms unique to CERN, or are they abstractions of well-known computer science or other algorithms?
I think a lot of them are based on more, fundamental, well-known ideas, but usually they have to be pretty tailored to what you're doing. So, like for example, something I work on a lot is tagging particular events from B quarks, which are a very difficult type of event to tag. And really, the real question is about tracking particles and reconstructing tracks very, very quickly and efficiently, which is just like a really hard game of connect the dots. But you need it. There's unique physics challenges to the problem that you might not see otherwise.
And usually for tracking stuff like that, we just use a pretty basic, at least at the level 1 trigger, we're looking at doing tracking just as a collection of straight lines, not even trying to do any sort of curve matching, because it just takes too long for the kind of time scale we're going for. And it's more easily implementable in FPGA boards, which are the fast electronics that we really need to use for this type of data. Yes.
It seems there's not a lot of space between the amount of time the data is saved versus the amount of time taken to fire a trigger and pull the data in. What percentage of the data that's triggered do you actually successfully process?
So the goal is really to save just the most interesting data. We don't need to save all of it. And I mean, it wouldn't even be beneficial to save everything. So I think the goal for the hardware system is to push your hardware as fast as it can go to try to make these decisions quickly so that it can know when an interesting thing has happened. And really then, I guess one of the limiting, the way you could speed this up is you could just make collisions happen more or less frequently. If your hardware isn't fast enough to keep up, you would need to slow the collision rate down. Otherwise, I guess your buffer would fill up and you wouldn't be able to save anything.
And in terms of efficiency of the triggering system, at least the sort of synchronization problem I mentioned earlier, it pretty much locks the detector up for a period of time. If something gets out of sync with the rest of the detector, you have to bring it all you have to stop, bring it, and bring it back up to make sure everything is in sync with each other. So this happens every once in a while for each detector, like every couple hours or so. And we lose data for a couple seconds during this, but it's really not. Our triggering system is very efficient in actually collecting the data that we attempt to collect.
So you actually collect almost 100% of
Yeah,
Yes, I would say the efficiency is greater than 97, 98%.
This is sort of a facetious question, almost, but not quite. Seems to me there's an opportunity, there's some selection bias. Clearly, you're only looking at things that look like the things you want to look at.
Yes.
Yes.
So there must be some null hypothesis reputation calculation going on. What's the probability that you're seeing random data through a filter that makes it look like what you want to see?
This is why we have multiple detectors.
Yes.
Why we have two separate collaborations who don't talk to each other, build completely separate machines, and then later compare their data.
Yeah.
Because then we can see, at least if we have some sort of bias in our search, that if we do it completely separately twice, then that's a pretty good indication that we actually found something.
Like, so for example, with the Higgs search, CMS also produced a 5 sigma result. But their search, even though they used some of the same channels, they didn't select their data the same way. Their detector, parts of it are built different, completely differently than Atlas. So it's run by the Atlas and CMS scientists are not supposed to share data. They don't, there's rumors, but
And they have completely separate Monte Carlo simulation,
Yeah.
completely separate detector simulation.
Mm-hmm.
But, it's like the question I asked about statistics.
Oh, okay.
Okay.
Experiments.
Yeah.
The
Yeah.
idea that you have enough-
Well,
you
I mean,
type-
so,
typing enough typewriters or
in a way, particle physics, in the way we know it, has been a field for about 70 years. And so when we're talking about these, the boring events, these ones where they sort of glance off each other and nothing that great happens, these are really low energy. But we've been studying lower energy particle physics for a very, very long time. The original detectors were much more simple, and they were looking at these sort of boring events, and they really understood them really well. So we do rely a lot on other experiments that have occurred in the past, if you want to understand how often certain processes occur, you rely on somebody else who's done that experiment in the past. And so we do take a lot of faith that we really understand the basics. We need to really, really understand the simple stuff. And that wouldn't be possible without a long history of experiments.
Yes, today's signals are tomorrow's background. That really rings true in our field.
Mm-hmm.
Yes.
This might be oversimplifying everything, but what I understand is that you have a very high-speed camera and you're trying to go through all the detections with the high-speed camera and see whether it can happen or not.
We have about 1 million cameras, but yeah, that's.
Those similar techniques happen in image processing. A lot of things people do today also in similar ways. Have you taken inspiration from this in terms of the machine learning that they have used in these kind of image processing, detect things like motion and those kind of stuff? Yes,
actually. So I know in the flavor tagging group, which I work in, one of the like I said before, one of the things you're really looking for is tracking particles, and you want to be able to recognize certain patterns over and over again. And so a group at Stanford wrote an algorithm that could do this you could basically take a 2D image of what the detector saw in a particular place and try to reconstruct it using image processing. And this worked great. But then they realized what they really want to do is process a 3D image. And so that was a little harder because we don't do image recognition on 3D images that much. You take a 2D picture on your phone or something. And so, but I think this is a pretty new effort in the LHC to try to take inspiration from techniques and problems that other people and other companies are handling and trying to apply them to physics. And I think I think the LHC has really been a lot slower to get on this than they should be. It's a lot of the older community of particle physicists, they don't think of themselves as coders. They think of themselves as physicists who have to code for their job.
And they all had to learn Fortran.
Yeah, and so but I think that's changing a lot. We just can't things just can't work the old way. So I would really like to see more collaboration with people outside the field.
Thank you.